Steam produced in a power plant boiler is used to drive a turbine which turns a generator to generate power. The process of converting water to steam in a boiler uses energy that's supplied by the combustion of fuel. Combustion in a boiler provides the heat necessary to convert water into steam. In order for combustion to take place, 4 elements must be present. These elements are oxygen, fuel, heat, and a chemical reaction. If any of these elements is missing, the process is incomplete and combustion will stop. For instance, if we remove the source of fuel from this flame by turning off the gas supply, combustion ceases. No matter how much heat and oxygen are present, the chemical reaction resulting in combustion will not occur without fuel. In addition to the 4 elements that are needed for any type of combustion, combustion in a boiler requires 2 additional elements to control combustion so that it's efficient. These elements are turbulence, to mix fuel and oxygen thoroughly, and time, to allow the combustion to be complete. Let's look at an illustration of a typical boiler to see how each of these elements fits into boiler operation. The oxygen that's needed for combustion comes from air supplied to the burners. At the burners, the air is mixed with fuel. Natural gas is the easiest fuel to use because it readily mixes with air. Oil must first be atomized, that is, broken into small droplets before it can mix with air. Coal often requires even more preparation. In most cases, coal must be pulverized into powder-like granules before it will readily mix with air. Regardless of the fuel used, a boiler's burners are designed to optimize the elements of combustion so that it will be as complete and efficient as possible. A boiler generally has many burners located around the boiler furnace to provide an even source of heat to convert water into steam. Typically, burners are located in a wind box, which evens out the flow of air so that each burner is supplied with approximately the same amount of air. A burner has 3 main parts: a fuel nozzle, an igniter, and 1 or more air registers. The fuel nozzle helps to create turbulence by spraying fuel into the boiler. The igniter provides the initial heat needed for combustion. After the fuel begins to burn, the heat needed to continue combustion is usually supplied by the flame in the boiler furnace. The heat from the igniter is no longer needed. The air registers provide a means for regulating the flow of air through the burner and help create turbulence. Once air, fuel, heat, and turbulence have been provided in a controlled manner, the chemical reaction of combustion can take place in an efficient manner. The time element of combustion is satisfied by the design of the furnace as a large open space in which fuel and oxygen have time to mix thoroughly and react completely. A boiler's fuel system consists of components that prepare the fuel, supply the fuel to the boiler, and burn the fuel. Let's take a look at a simplified illustration of the fuel system for a coal-fired boiler to see how a typical system operates. This fuel system includes a pulverizer, a coal feeder, a primary air supply, an exhauster, burners, and a secondary air supply. Small chunks of coal enter the top of the pulverizer from the coal feeder. In the pulverizer, they are ground into the powder-like granules that can mix thoroughly with air. Primary air, which has been heated, enters the side of the pulverizer. The primary air picks up the finely ground coal, dries it out, and carries it to the burners. An exhauster is used to assist primary airflow from the pulverizer to the burners to help move the coal dust. The coal and primary air enter the burner through the fuel nozzle and mix with secondary air. The secondary air enters each burner from the wind box through the burner air registers. The registers cause the secondary air to swirl around, adding to the turbulence that's caused by the fuel nozzle. The heat needed to start combustion comes from an igniter. One common type of igniter used in coal-fired boilers consists of a miniature oil burner that can be lit by a device that is similar to a spark plug. The electric spark ignites the oil, which in turn ignites the pulverized coal. For example, in one type of oil-fired boiler, oil is sprayed out through the fuel nozzle, which is designed to atomize or break up the oil into very small droplets that can mix readily with air from the air registers. In a typical natural gas burner, the gas is fed under pressure from the gas supply to a burner manifold. From the manifold, the gas flows into pipes called gas spuds. Holes in the ends of the spuds direct the gas into the boiler furnace. Some boilers have burners that can be used with more than one type of fuel. For instance, this burner has both gas spuds and an oil nozzle. As an operator, you may be responsible for monitoring instruments to ensure that the relative amounts of fuel and air in a boiler furnace are correct. You'll probably hear these relative amounts referred to together as the boiler's fuel-air ratio. For coal-fired boilers, the fuel flow is regulated by adjusting the speed of coal feeders that supply coal to the pulverizers. For oil-fired and gas-fired boilers, fuel flow is controlled by adjusting the positions of valves in the fuel lines. For all three types of boilers, airflow is regulated by positioning vanes or dampers in the air supply lines to or from the forced draft fans, or by regulating the speed of the fans. Changing either the fuel flow or the airflow changes the fuel-air ratio in the boiler. The correct ratio is often maintained by monitoring the amount of oxygen going out the boiler stack. If fuel and air could be mixed perfectly, you could adjust the mixture so that exactly the right amount of oxygen would be supplied to allow the fuel to burn completely. All of the oxygen would react chemically with the fuel, and no oxygen would exit through the stack. Unfortunately, however, achieving a perfect mixture of fuel and oxygen is impractical. In practice, how do you think the fuel-air ratio is adjusted to make sure that all of the fuel is burned? By making sure that all of the fuel is burned, you reduce the possibility of an explosion caused by unburned fuel building up in the boiler or in the stack. Since excess air is supplied to the wind box, there should always be excess oxygen going out the stack. Most boilers have an instrument that measures the level of the excess oxygen near the boiler outlet to the stack. Part of a boiler operator's job is to monitor the readout from this instrument and adjust the airflow when necessary to make sure that the excess oxygen level stays within the acceptable range for the plant. We've used two terms that you'll often hear around the plant concerning the fuel-air ratio. They are excess oxygen and excess air. In many plants, there is a distinction between these terms. Excess oxygen is the term used to describe the oxygen going up the stack. Excess air, on the other hand, refers to extra air supplied to the wind boxes above the theoretical minimum amount needed for complete combustion. In this topic, we took a look at the elements needed for efficient and clean combustion in a boiler, and we identified the parts of boiler fuel systems. We also looked at operator responsibilities associated with maintaining the proper fuel-air ratio in a boiler. Now let's try some practice questions. The fuel nozzle helps to create turbulence by spraying fuel into the boiler. Primary air, which has been heated, enters the side of the pulverizer. The primary air picks up the finely ground coal, dries it out, and carries it to the burners. Excess oxygen is the term used to describe the oxygen going up the stack. Excess air, on the other hand, refers to extra air supplied to the wind boxes above the theoretical minimum amount needed for complete combustion. As fuel burns in a boiler furnace, air is brought into the boiler to support combustion. During the combustion process, hot gases called flue gases or combustion gases are produced. The hot combustion gases flow out of the boiler. The combustion gases that leave the boiler furnace contain a great deal of heat. In most boilers, as much of this heat as possible is transferred to steam, boiler feed water, and incoming air. This way, less fuel is needed in the boiler furnace and the efficiency of the boiler is increased. Let's take a more detailed look at a typical coal-fired boiler to see how this works. Airflow starts at a forced draft fan that takes in air at atmospheric temperatures and pushes it to the boiler. In the boiler, the air passes through an air preheater where its temperature is raised to about 500 degrees Fahrenheit. There are two common types of air preheaters, rotary preheaters and tubular preheaters. In a rotary air preheater, heat transfer is accomplished by the use of a rotating metal drum. The drum contains a number of plates and is divided in half by a stationary seal. The seal helps keep the incoming air, which passes through one side of the drum, separate from the outgoing combustion gases, which pass through the other side of the drum. As the drum rotates, the metal plates move from the stream of hot combustion gases, where the plates heat up, into the stream of cooler incoming air. This causes some of the plates' heat to be transferred to the air. In some systems, steam is used in the tubes instead of combustion gases to heat the air. Regardless of the air preheater's design or the medium used as a source of heat, the heating medium and the air don't come in direct contact with each other. After it passes through the air preheater, the heated air is split into a primary air supply and a secondary air supply. The primary air flows to the pulverizer, where it's used to dry pulverized coal and carry it to the burners. And the secondary air flows to the burners, where it rejoins the primary air and helps to support combustion. When the fuel and air mixture is ignited in the burners, the flame burns at approximately 3,000 degrees Fahrenheit. The chemical reaction of combustion consumes most of the oxygen in the air and produces hot combustion gases which flow out of the boiler furnace. As the combustion gases rise in the boiler furnace, their temperature decreases to about 2,000 degrees Fahrenheit as heat is absorbed by the tubes surrounding the furnace. By the time the combustion gases enter the area of the gas flow path that contains sections of boiler tubes called superheaters and reheaters, their temperature has dropped to about 1,800 degrees Fahrenheit. Superheaters and reheaters are heat exchangers. Their purpose is to raise the temperatures of the steam produced in the boiler so that the steam can do more work. Steam flows through the superheater and reheater tubes. In this example, the temperature of combustion gases drops about 1,000 degrees when the gases transfer heat to the steam. The gases leave the last superheater at about 800 degrees Fahrenheit and pass on to another heat exchanger called an economizer. The economizer uses heat from the combustion gases to raise the temperature of feed water that is on its way to the boiler. Feed water flows through the tubes of the economizer, and the combustion gases flow around the tubes. When they leave the economizer, the combustion gases have cooled to a temperature of about 650 degrees. The gases then pass through the air preheater, where their temperature drops another 350 degrees. Finally, the gases flow through an induced draft fan and leave the boiler at about 300 degrees. The boiler in this example is a balanced draft boiler because it has both a forced draft fan, which pushes air into the boiler, and an induced draft fan, which pulls combustion gases from the boiler furnace. Other boilers, often called pressurized furnace boilers, have only a forced draft fan. The incoming air from the forced draft fan pushes combustion gases through the flow path and out of the stack. Combustion gases contain byproducts of combustion in the form of gases and unburned solid particles called particulates. These byproducts must be removed before the gases are discharged in order to avoid damage to equipment and to the environment. Harmful byproducts are kept under control in the boiler by proper boiler operation. For example, sulfuric acid, which is very corrosive, can form on the air preheater when sulfur trioxide in the combustion gases combines with water. To prevent the acid from forming in the gas flow path, combustion gas temperatures are kept above the dew point. The dew point is the temperature at which water vapor in the gas flow path will condense into a liquid. If the water vapor does not condense, the danger of corrosion to the air preheater is greatly reduced. Eventually, combustion gases are released into the environment. To protect the environment, the gases are treated to remove harmful substances before the combustion gases are discharged. Three commonly used devices for removing harmful byproducts from combustion gases are scrubbers, electrostatic precipitators, and bag houses. Some scrubbers can remove both particulates and gases, while precipitators and bag houses remove only particulates. Let's take a look at how each device operates. Scrubbers can be classified as wet or dry, depending on what they pass the combustion gases through. In a wet scrubber, combustion gases are passed through liquid sprays. Particulates in the combustion gases stick to the liquid and collect in the bottom of the scrubber. The liquid spray also separates sulfur oxides from the combustion gases by absorption. The sulfur oxides are absorbed into the liquid, which falls to the bottom of the scrubber. Both the particulates and the sulfur oxides are removed from the scrubber along with the spent liquid. That's basically how a wet scrubber works. The powder, often called sorbent powder, absorbs the sulfur oxides, removing them from the combustion gases. The combustion gas and powder mixture is then passed on to a dust collector, where the powder, along with other particulates in the combustion gases, is removed. The dust collector is often either an electrostatic precipitator or a bag house. Electrostatic precipitators remove particulates using an electrical charge. An electrostatic precipitator has several power sources that create a positive charge on a series of metal plates and a negative charge on a series of wires located between the plates. As the combustion gases pass through the precipitator, the particulates pick up a negative charge from the wires and are attracted to the positively charged metal plates. Devices called wrappers are used to physically jar the collected particulates loose from the plates. The particulates slide into a collection hopper in the bottom of the precipitator. From there, they can be removed from the system. A baghouse, on the other hand, uses a series of porous bags installed in the gas flow path to physically filter particulates from the combustion gases. As the combustion gases are drawn through the baghouse, particulates are trapped on the surfaces of the bags, while the rest of the combustion gases pass through. In this topic, we followed the air and gas flow path through a typical boiler, and we saw how the heat contained in the combustion gases is used in a boiler. We also looked at some of the equipment that is used to remove particulates and harmful gases from combustion gases. Now try some practice questions. In a rotary air preheater, heat transfer is accomplished by the use of a rotating metal drum. The drum contains a number of plates and is divided in half by a stationary seal. The seal helps keep the incoming air, which passes through one side of the drum, separate from the outgoing combustion gases, which pass through the other side of the drum. As the drum rotates, the metal plates move from the stream of hot combustion gases, where the plates heat up, into the stream of cooler incoming air. This causes some of the plates' heat to be transferred to the air. By the time the combustion gases enter the area of the gas flow path that contains sections of boiler tubes called superheaters and reheaters, their temperature has dropped to about 1800 degrees Fahrenheit. Superheaters and reheaters are heat exchangers. Their purpose is to raise the temperatures of the steam produced in the boiler so that the steam can do more work. Steam flows through the superheater and reheater tubes. A baghouse, on the other hand, uses a series of porous bags installed in the gas flow path to physically filter particulates from the combustion gases. Boilers have a number of vents, drains, and blowdown valves that are open to allow air, water, and contaminants to be removed from the boiler. As an operator, you should know when each vent, drain, and blowdown valve should be opened and when each must remain closed. Vents, such as this boiler drum vent, are usually located on the tops of components. Vents are usually opened only during a boiler startup, when there may be a great deal of air in the system. The vents are needed to bleed air from various components. When enough time has passed to allow all of the air to escape from the system, the vents are closed. Drains, on the other hand, are usually opened only when components are shut down. Drains are used to remove unwanted liquid and are typically located at the bottoms of components. In most cases, opening drains during boiler operation can cause problems. For example, opening a water wall drain while the boiler is operating could upset the natural flow of water through the boiler's water flow path, and the boiler tubes could overheat and rupture. Blowdown valves are a kind of drain that may be opened during boiler operation. One common type of blowdown valve on a boiler is a surface blowdown valve, which is located near the normal water level in the boiler drum. Contaminants commonly collect on the surface of the water in the drum. The surface blowdown valve can be opened periodically to remove or blow out water containing these contaminants. During the operation of most boilers, especially coal-fired boilers, soot builds up on water wall tubes and other components. This soot buildup blocks efficient heat transfer, and it must be removed if efficient boiler operation is to be maintained. Soot blowers remove soot by blowing it off of the tubes with a medium such as compressed air or steam. A typical soot blower is made up of a lance tube with nozzles, a feed tube, and a valve. When the valve is open, a blowing medium is sent through the feed tube under pressure and discharged through the nozzles in the lance tube. There are two general types of soot blowers found in most boilers: wall soot blowers and long retractable soot blowers. The main difference between the two types of soot blowers is the distance they can be inserted into the boiler. Wall soot blowers can be inserted a short distance into the boiler furnace to remove soot from the water walls. Long retractable soot blowers, on the other hand, can often be inserted more than half the width of the boiler. They are used to remove soot from superheaters and reheaters. In most cases, both types of soot blowers are retractable, so that the lance tube can be inserted into the boiler while soot blowing is in progress, and then removed when it's not needed to prevent heat damage. The soot blowers are typically programmed to operate in a predetermined order to ensure proper cleaning of the boiler tubes. However, there may be occasions when you'll need to manually bypass a certain soot blower or manually retract a soot blower that will not respond to automatic control. In this topic, we looked at some of the typical vents, drains, blowdown valves, and soot blowers found on boilers and described their purposes. Now let's try some practice questions. Boilers have a number of vents, drains, and blowdown valves that are open to allow air, water, and contaminants to be removed from the boiler. Soot blowers remove soot by blowing it off of the tubes with a medium such as compressed air or steam.